Hello, welcome back to your Theory 2. Okay, so we will now proceed in your Module 2. It is now the analysis of statically indeterminate structures, which we will be discussing here. The method, which is what we call as the consistent deformation. Okay, so analysis of your indeterminate structures using consistent deformation method. So what is consistent deformation method? Okay, so this method was introduced by James C. Maxwell, okay, in 1864. And this method of analysis involves removing redundants. Okay, so again, if we'll try to recall what is redundants, these are the excess, okay? If you are talking about the excess reactions or restraints, member forces, or members or reactions in your, forces in your reactions, these are the redundants if that is the excess from the equations of equilibrium. Okay, so let's say you have a simple beam, and of course, for determinate structures, you should have only three reactions. And let's say you have now a second degree of indeterminacy. It means that there will be two redundants. Okay, so in this method, which is what we call as the consistent deformation, we are going to remove these redundants to make your system determinate. Okay, so whatever the redundant is there, let's try to reduce by removing these redundants to make it determinate. And then of course, we cannot just remove that one. Of course, there should be always an effect of that. So the redundants will be applied to the resulting determinate structure. Okay, if you will try to remove let's say you have two excess reaction, then you are going to remove that one, so that will become determinate structure. However, we are going to put this back, these redundants that we remove, as an unknown forces. So instead of reaction, that will now become an unknown forces. And then of course, we will try to create a compatibility equation. So if we say again compatibility equation, these are equations that will be formed based on your deformations. Okay, so coming from deformations. So we will try to create number of compatibility equations that are the same with the number of redundants that we remove. Okay, so we will try to create, if let's say we have two redundants, we remove two redundants, then we need to create, or we need to formulate two compatibility equations. And for us to solve these redundants, these unknown forces, using these compatibility equations, and then apply that one as a force in your determinate structure, and then solve the remaining reactions or restraints using the equations of statics, the three equations of equilibrium. Okay, so that is how we will apply consistent deformation method in analyzing an indeterminate structure. Okay, it could be internally or externally. As long as that is indeterminate, remove redundants. Okay, and then formulate equations corresponding to the number of redundants, and then solve the redundants using these compatibility equations, and then apply it back as a force in your system, and then solve the rest. And of course, that resulting forces and reaction will be the reaction of your indeterminate or your original structure. So by the way, we need to consider here, if you are trying to choose, by the way, let's say you have five reaction in your system. Which one of these five reactions are you going to use as redundants, or are you going to consider as redundants? Actually, that is up to you. As long as if you will try to remove these redundants, the determinate structure will be still stable. Okay, so I will explain that one. So for example here, okay, let's try to consider this indeterminate structure here. That is fixed and fixed on both sides of the beam. Then of course, if you will try to look at the reaction, then there will be three reaction in this A, and then three reaction at B. So actually there are three unknowns, and if you will try to use the three equations of equilibrium, there will be three redundants. Okay, so the degree here is third degree, indeterminate to the third degree. So there are three redundants. Therefore, we need to create three equations. If ever you are solving this one, you need to create three equations of compatibility, or compatibility equations, to solve the three more, and then apply it back as a force in your system. Okay, so let's say I will choose three redundant. Okay, so how will you choose that one? It's up to you. So in this case, there are two possibility here. Okay, I presented you a two possibility, but there are more possibility if you will try to look at the system. So let's say the first case is that I will try to remove the two moments, and then of course one of the forces. But for me, let's say to make it simpler, why not remove the two moments and the one of the horizontal, so that this will be my resulting determinate structure. So what do I have here? If I will remove the moments here, of course that will not be fixed already. So if I will remove the moment there, that will now become a pin, since that is just supporting horizontal and vertical restraint, or horizontal and vertical motion. So this will become pin. However, if I will remove here too, let's say I will remove the moment and then the horizontal restraint or reaction here, then that will just be reacting against vertical, so that will serve as a ruler. So how many, this color orange here will be actually now your resulting reaction of the determinate structure. So 1, 2, 3. So you have now only 3 reactions. So we can solve these 3 later on if you already know these values of redundant that I removed. And I will apply that one as a value or forces on this determinate structure. Then we will solve the rest of these 3 reaction using the statics, the summation of horizontal, vertical, and summation of moments. Okay, so the question there is, how will I create or how will I solve these 3 redundants that I remove? Again, as I've said a while ago, we will try to create compatibility equations, and these compatibility equations will be coming from deformations. That's why we recall your deformation in your module 1. What is deformation? These are the rotations and deflections. So how will I create the compatibility equation corresponding to the moment that I removed here? So originally that is fixed. So in the actual beam or the original beam, at this point, at point A, that will never rotate, or that will not rotate because that is originally fixed. So even if I will remove that one, I will assume that that is just a pin. However, it is originally that there is no rotation since that is fixed. So we know that at A, the rotation should be 0, or that theta A is actually the slope of the tangent. So since there is no rotation, the slope of the tangent is 0, or the tangent to that point A is horizontal. Okay, so we will use this notion or this idea to create the compatibility equation in this part where we remove the moment. And as we go on the other side, the same, since that is originally fixed, and we know that that is originally fixed, therefore the rotation there should be 0 also. Okay, the tangent should be horizontal at point B. And then what else? Since that is fixed also, in your determinate structure, it looks like ruler, so it means that there is no restraint horizontally, but because again, originally that is fixed, there is no deflection. Okay, there is no deflection horizontally. So your deflection horizontally is also 0. So that is another idea where we will be getting your compatibility equation. So using theta equals 0, one compatibility equation, theta b equals 0, another compatibility equation, and of course your delta h at point B equals 0 also. This is the third equation. So using these 3 compatibility equations, we can solve these 3 the redundants. Okay, and once we know these values of the redundants, we will apply it as forces, whatever the values of this. So that will serve as forces together. If there is an external loading, then the external loading in these forces will serve as a load for you to compute your 3 remaining reactions. Then once we have all of this, we will put back these redundants and that solve reactions to the original structure. Then whatever the values of these 6 reaction, then that will be the reaction of our indeterminate or your original structure. Okay, so there is another case here wherein, what if I will remove all the 3, I will make all these 3 reaction at B as my redundant. So the remaining reaction will be these 3 at point A. So that could also be. So it will now become, it will look like a cantilever beam. Or in this original tree reaction here, which will be my redundant, we will be getting this one by again compatibility equations. And again, how will we get that compatibility equations? We know that that is originally fixed, so the rotation at B is 0. And also that is fixed, so there is no deflection horizontally, and also there is no deflection vertically. So using these three idea, we will create the three equations of compatibility, and then we will solve these three redundants, apply it as a load, including your external loading. We will solve these three remaining reaction, and then that will be the reactions of the entire original structure. Okay, so that is consistent deformation method. So what am I saying a while ago is that in choosing your redundant, you should consider also that the resulting determinate structure should be stable. So if you'll try to look here, the first case or the first possibility, if I will remove the moment, and this horizontal here, that will still be stable, isn't it? That will not transform, or that will not translate, or that will not move horizontally, since that is pin here, so that is holding it horizontally. And of course there are reactions at both ends of this beam, so that will not rotate even if there is no moment reaction here, because there is a ruler here. It means that will not rotate clockwise or counterclockwise, so your beam is still stable. Okay, because if you'll try to make this just choose any redundant, and your structure will now be unstable, you will end up later on with equations as your answer. You will just be circling around and solving the equation going back to itself, if that is the case. Okay, or you cannot create other equations of compatibility, because again, in the first place, your resulting determinate structure is unstable. Okay, or even if you solve the redundance, then solving the remaining reaction, since that is unstable, you cannot do it. So if you try to look at the second possibility, this is still stable, because since there is a restriction or restraint horizontally, then that will not move horizontally, and vertically there is a restraint. And talking about rotation, that will not rotate because there is a restraint of moment here at point A. So even if you will try to apply here load, that will not rotate because that is already fixed there. So again, this is still stable. Okay, so that is consistent deformation. So we will try now to, I will just present here the procedure, but actually if you'll try to follow it one by one, there are a lot of steps, but let's just take it generally. Okay, so first step or procedure in analysis of this using your consistent deformation is that select your redundants based on the degree of indeterminacy. So if your structure is indeterminate to the third degree, then it means there are three excess restraints, so there will be three redundants. And in choosing, of course, in choosing these redundants, you need to consider the stability, as what I'm saying a while ago. And then number two, we will try to draw the resulting determinate system, of course, and do not forget to include the removed restraints as a force or couple. If your removed redundant is a moment, then that will be a couple force, or if you say couple, that is the same as moment. That will be a moment applied. But if you remove there a reaction force, then you will be applying redundant as a force. Okay, so that is your second procedure. Then of course, once you have already your determinate system and then your redundants in your figure, create your equation of compatibility, or your compatibility equations. Again, basing on whatever is the original setup of your indeterminate structure. So again, based on the deformations of your original system, okay, so that is where we will be basing. Formulate the compatibility equations and solve for the redundants. Okay, if there are three redundants, then you need to create three equations of compatibility, and then use these three equations of compatibility to solve these three redundants. And of course, as I'm saying a while ago, this is what I'm saying, the number of redundants should be the same as the number of compatibility equations. Then once you already solve that redundants, then apply that one into your determinate system and then solve for the rest. Okay, So determine the remaining restraints using the statics of equilibrium. Why? Again, since that is simplified as determinate structure, then whatever reaction there is, you can solve that one by statics. Okay, your equations of equilibrium, summation of force horizontal, vertical, and summation of moments at any point. So that is our procedure. Remove the excess, and then solve that one by compatibility equations, apply that one as a force, and then solve the rest of the restraints, and that will now be the total restraints of your indeterminate structure. That is consistent deformation method. We call it deformation because we are solving the other restraints using the deformations, the deflections, and the rotations. Okay, so that is why we call this one consistent deformation method. Okay, so there are types of structures in it. We can just have a simple beam, a frame, or a truss. So let's try to discuss this one by one. So in our first unit under this module 2, let's try to apply consistent deformation method on beams. Okay, so let's start with beams. So in this unit, we will be analyzing indeterminate beams using your CDM, or that is the consistent deformation method, and of course to formulate compatibility equations based on the type of supports. So again, if you discuss this one, creating your compatibility equations, if you will try to recall your moment area, your methods of determining deflections and rotations, you will be needing these ones here in creating your compatibility equations. Okay, so let's try to discuss these beams by having examples. Okay, so let's try to have this example number 1. Okay, it says there that determine the reactions of the beam shown below using consistent deformation method. Okay, so if you'll try to look here on the beam presented below, we have here a 20-meter long beam, and we have here a support on the other end, on the one end to be fixed, and on the other end to be ruler, and there is an internal support which is ruler also. So if you'll try to count the reactions for us to determine how many redundants or what is the degree of indeterminacy, if you'll try to look at this, there will be 3 reactions here since that's a fix, and there is 1 and there is another here since these are ruler. So 3 plus 2 will be 5. Therefore, we have there only an available 3, and there is no equation or condition equation. Okay, there is no internal hinge or internal ruler here, so there is no other additional equations for statics. So we only have here 3 equations of statics, and we have there 5 reactions. Therefore, there will be an excess of 2, and that is the degree of indeterminacy. It means that there will now be 2 excess, therefore there will be 2 redundants. So if you will try to break down this one, okay, there will be a moment, horizontal reaction, vertical reaction, a vertical reaction, and vertical reaction. There are a lot of ways again. There will be a lot of possibilities for us to choose your redundants, but actually it doesn't matter. So let's say, okay, let's say I want to make this one as a pin and make this and leave this one behind. So I will remove this one, so that will be one of my redundant, and of course since I will make that one as a pin, one of my redundant will be the moment in your point A. Okay, so I will release the moment here, that will become pin, so your moment reaction will serve as redundant, and I will release this internal ruler here, internal support ruler, so that will serve as my second redundant. So I will make it as color red so that the orange will just be my reactions. So this is the case that I choose. Okay, and if you try to look at this, you need to consider again the stability. It will not move horizontally since that's a pin, and it will not rotate since there is a reaction or there is a vertical reaction on the other end. So we're good. This is stable. So again, this is your external loads, 120 and 120 in between your supports, exactly in between. Okay, and then therefore there will be 2 redundants. So it says there that I need to create 2 equations of compatibility to solve these redundants, and then later on I will apply it. Whatever the values of MA, I will write that as M sub A since that is the moment at A, and CV since that is a vertical reaction at C. So whatever the value later on that I will be solving coming from my compatibility equations, I will apply it as a load, okay, together with your 120 kilonewtons. And then I will be solving whatever the values of E sub of EB, AB, and then AH. Then later on, I will put back all of these reactions back to the original indeterminate beam. Then that is now the reactions of our indeterminate beam originally. Okay, so we are done. This is my first procedure. I choose my redundance, and that is the moment and the vertical reaction at C. Okay, and I already drawn that one, and I already checked that that is stable. Okay, so second is formulate the compatibility equation. So there are two redundants, therefore we need to have two equations of compatibility. So first, isn't it, as I have said, you need to know the original situation. If that is originally fixed, then at that point the rotation should be zero, isn't it? If you'll try to recall your deflections and your rotations in your deformation of beams or structures. Okay, so that is what we will be using to create your compatibility equation. Okay, so let's start with your point A. Since I released the moment here, even if that look like a pin, however, originally that is fixed, so therefore the rotation at point A should be equal to zero. Okay, so I will use that as as an idea to create my equation. So what will I do here is that, okay, since this is my explanation a while ago, okay, so the rotation there should be zero since that is fixed. So if you'll try to recall your what we call this one, rotation or deflections in your deformation, there are a lot of ways to get this one, but I will be showing you the commonly used, which is the, of course, the conjugate beam, isn't it? And of course we will try to break this down into components. So what we are going to do here is that if you'll try to separate and then look at the effect, okay, if you'll try to do it so as using superposition method, okay, if that is discussed or not in your what to call this one, theory 1, superposition method means we are going to analyze the system part by part, okay, load by load. So what will I do? I will try to analyze the effect of the external load only, and then I will try to analyze the effect of my first redundant, and then I will analyze the effect of my second redundant. That is how will I end up with my compatibility equation. So first, let's start with your external loading. So let's try to understand how that external load will affect our resulting determinate beam. Okay, but you should know that the rotation at A is zero. So let's say I will only apply there the external loads. So this will be my first beam here. So I will try to break down our situation into separate situations, and then later on we will use this one to create our compatibility equation. So first, the effect of your external loading. So that is, these are the two 120 loads directed at the in between, or loaded at in between the reactions originally. So if you'll try to load that one 120 and 120 here, this could be the deflection. So draw the elastic curve. So this could be my elastic curve or the deflected beam. Then what happens there is that you have this angle here. Since we are talking here of zero angle at A, then we will investigate the angle at A. So at point A, that will be my slope, or that will be my rotation. So I will put that as theta AL. So what does that mean? I describe it here. It means that that is the rotation at A, since we are investigating point A, due to the external loads. That is because of the external loads. Okay, so that is your sub L there. So again, theta A sub AL means rotation at A due to the external loading. Okay, we need to have here subscript to differentiate one rotation from another, since we try to break down this situation. Okay, so that is what happened if that is just the external load. Now, since that is the deflection or that is the rotation because of external load, if I will try to apply back your redundance, then that should put it back into zero rotation. See, because that is the actual scenario on your fixed beam, fixed end, isn't it? There should be no rotation. So if that is only my external loading, there will be a rotation, which is, if you will try to consider sign conventions, this will be a negative. Why? Because the tangent from the point that we are investigating to the original location of the beam or orientation of the beam is counterclockwise. Okay, so let's say we will follow clockwise to be positive and counterclockwise to be negative. Going up is positive, down is negative. Right is positive, left is negative. Okay, so since we are used in following your Cartesian planes. Okay, and then in rotation, clockwise is positive, counterclockwise is negative. Okay, but if you will try to assume the other way, why not? No problem with that, as long as you will stick to one assumption. Okay, so you will expect here a rotation which is negative due to the external loading, since again from the tangent to that point going to the original beam, that is counterclockwise. So we will be having here a negative, but let's say we do not know, since we just assume that this will be the deformations. So let's just assume, okay, we do not know, let's say we do not know that this is the case. So all I need to do here is that summate that rotation due to the external load. So that will be my theta A sub L here. And then what else? If I will try to apply my redundant, if you have more than one redundant, you need to apply this one by one. Okay, one by one redundant. Do not apply 2 or 3 redundants at the same time, since you cannot create you cannot analyze the behavior in each redundant. So let's try to start with my redundant M sub A, or the moment. My moment redundant. So if you try to put here, this will be the effect. Okay, for example, we do not know that is the moment there. Okay, we do not know. So I will just assume that that will be the flow of my, or the direction of my moment. So if that is the direction of my moment, then that could be the deflected beam. Okay, that will now be my elastic curve. Wherein the rotation will now be positive, because if I will draw a tangent at point A, that angle going to the original beam is clockwise. Okay, so if that is negative and this is positive, now we are trying to cancel out the effect of the external loadings. That's a negative, and we ended up with a rotation due to the redundant MA to be positive. It will try to cancel this one. Okay, and then later on, of course, we will go to the other redundant, since we have one more redundant. If I will apply there my redundant C sub V, okay, this could be my reaction, or this could be my elastic curve. This could be the deformation of my beam. So what will be the rotation also there is also a clockwise. From the tangent to the beam is clockwise, so that is also a positive. Therefore, if I will try to combine this positive due to MA and positive due to CV, then that will cancel out the negative effect of your external loading. So again, I will satisfy that if I will summate all these rotations from the external loading, from the redundant MA and then redundant CV, you should end up with 0, because that is originally a fixed support. Okay, that is where we are using this idea in your original beam or indeterminate structure. Okay, so again, you need to consider here sign conventions. So I consider that clockwise is positive and then counterclockwise is negative. And also, by the way, your redundants, we are not sure if those are the correct directions. So since I assume that that is the direction, then let's just take it as is. If later on we will solve that one, if we will solve the values and we will end up negative, the value will still be the same, but the negative only means it is the opposite direction. So for example only, okay, for example only, if we ended up with a value of CV to be negative, then it means that your CV is not going up, rather that is going down. Example only, okay, but we will try to figure that out later. However, if you are used in doing this one again, if you are used in assuming direction, you might target all the correct direction, so you will end up with all positive answers. But again, there is a negative that is the same value but opposite direction. Okay, so we have here one more concept that I need to insert, which is actually from previous topics of your theory 1. Another method of analyzing determinate or indeterminate structure, we call this one the unit load method. Since again, we do not know in the first place, we do not know that MA and CV. In the first place, we do not know those values. So how can I get that rotation AA and rotation AC if in the first place I do not know the value of the load? So we cannot proceed. Okay, we will be stuck. However, we have this unit load method in your theory 1, wherein if we will try to assume, or if we will try to consider, if that is a moment, we will consider there unity or one unit of moment, and if that is a force, we will consider 1 unit of force. Then the behavior, whatever the behavior of that beam, will be the same as the behavior if we will try to apply the entire value of the load. Only that the intensity will just be multiplied. Okay, let's say I will apply here 1, let's say, since we have here a kilonewton and meter units, so your moments will be expected to be kilonewton meter. So let's say I will apply a 1 kilonewton meter here. Let's try to evaluate what is the effect in the rotation. Then that effect, later on, if I will know that MA, I will just multiply the effect of, or the MA to the effect of 1 moment or 1 unit moment. Then that will be the effect of the entire moment A. Okay? The same here, the same idea in your C sub V. Since we do not know that one, we need to assume, let's say, I will consider here 1 kilonewton since we have a kilonewton here. So I will consider 1 kilonewton. And then let's try to figure out what will be the effect or what will be the rotation on the resulting beam. And then the value there later on, we will multiply with the value of C sub V, and that will give us the entire effect of the entire load or the entire force C sub V. That is the idea or the concept of your unit load method. Okay? So again, since we do not know these values, we cannot use directly. Okay, by the way, again, let's try to understand my subscript. Okay, a while ago, that is theta sub AL, because we are talking about rotation at A due to the external loading. That is theta sub AA, it means that is the rotation at A due to the redundant at A, since we are considering here the redundant which is located at point A. So again, rotation at your point A due to the redundant at point A. So that is the meaning of your sub AA. And then that sub AC is still we are considering the rotation at point A, but that effect is due to the redundant at point C. Okay, that is your redundant at point C. So that we will differentiate these values of rotations. Okay, so again, that is your subscript. And then of course, in this one, unit load method, the effect of the total, we'll try to break this down into a unit, okay, into a unit load. We call it a unit load since we are considering a unit moment or a unit force, okay. Since we are having here a unit moment, so we will apply here, a moment. We will try to apply here a unit moment, and then whatever the value of rotation here, that is your F sub AA. It means that is the rotation due to unit load, okay, applied instead of that moment A. And then of course the effect of that, multiply that one with your MA, which is actually an unknown, then that is the total effect, theta sub AA. So instead of having their theta sub AA, I will change that to the effect of one moment multiplied to the unknown moment. Okay, so that will be replaced there instead of the theta AA. The same here. That is the rotation. This FAC is the rotation due to 1 unit force. 1 unit force, since we do not know again C sub V. And then whatever the effect of that 1 unit force multiply that one to the value of the force itself. Then that will be the total effect on point A. So instead of writing theta sub AC there, I will change that to F sub AC times the C sub B. So you will end up here now with your one compatibility equation. So again, how did we ended up there is I tried to analyze the effect of each loading. Okay, the external load alone, okay, the external loads alone, and then the redundance individually. What is the effect of that on your beam? And if you will try to summate all the effect of that, since we are talking about a point, summate all the effect of that, that should be 0. The rotation, summation of the rotations in each individual cases should be equal to 0. Why? Again, why? Because originally that is supported using a fixed support at point A. So there should be no rotation at point A. Okay? So that is the compatibility equation at point A. And we will be getting, since we have two redundants, we need to have two compatibility equation. So I only get one from point A due to the redundant MA. I will try also to get another compatibility equation at point C due to our redundant here at point C. So this will be the next slide. Okay. Of course, we will not be considering here rotation, since actually that is the supported by a ruler. Originally, that is supported by a ruler. But even if that is just a ruler, if we will not talk about rotation, let's say I will talk about deflection, then even if that is a ruler, that will never deflect because that is still a support. That is a support vertically, so that will not deflect. We are talking now about deflection instead of rotation. So at point C, where that redundant CV is applied or is released, even if that is released, if you will try to go back to the original indeterminate structure, that should be still no deflection or zero deflection because there is a ruler there originally. Okay, so that is where I will create my second compatibility equation. So again, the idea there is that the deflection at that point C should be 0 since that is located at a support. That is what I'm saying a while ago. Okay, so how will I end up with the compatibility equation again? Just like a while ago, let's try to understand the scenario one by one. First is, of course, the effect of the external loads. Okay, if I will try to apply the external load, a while ago, what we investigated is the rotation at A, since that is where we are getting the compatibility equation. But since we are getting a compatibility equation at point C due to deflection, then what we are going to investigate here is the deflection at point C. Okay. So if I will try to apply my external load, the 120 kilonewtons, then this could be again the deflection of my beam. Or this could be the deformation, or that is the elastic curve. Then again, the vertical gap of the original beam to the deflected beam is the deflection due to the external loading. So let's write that as delta C sub L. Again, what does that mean? That is the deflection at point C due to the external loading. So your second L there is means due to the external loading. Okay. So again, since we assume that the sign convention of vertical is going up is positive, down is negative, so we will, let's say if this is the correct assumption, then that should be a negative deflection. The deflection due to the loading should be negative, which is true because even if you try to analyze this one, the load is going down, so that will deflect the beam upwards, or it will open, or it will concave upwards. So the beam will go down and the deflection is a negative because originally that is higher, so that will go down. So your deflection is negative. Okay, so that is the effect of our external loading. How about if I will apply my first redundant, MA? Again, I will apply that. This will be the elastic curve. So that could be my shape of my beam, deflected beam or deformed beam. So we are still talking about the deflection at point C. So what happens there is, if I apply that moment in that direction, since that is my assumption a while ago, that will that will bend your beam this way. So the deflection here is positive because that is originally here and that will go up. So we have now a positive deflection, which will actually trying to cancel that negative deflection here. And then if I will try to apply again my second redundant here, this could be my deflection. Again, this could be my elastic curve. Since we are again still talking about the deflection at C, what happened here is that that will deflect going up. So again, another positive deflection. So look here again, the effect of the load, that will go down. But the effect of our redundant, it will put it back. Why? Because that should be actually zero deflection. Because originally there is a ruler here. So if I will try to summate all these deflections of these three cases, then that should end up to zero. Okay, so that is the idea that we are trying to satisfy, and that will give us the second compatibility equation. So again, your deflection at C due to the external loading plus the deflection at C due to the moment or the redundant at A, and plus the deflection at C due to the redundant at C, then that should be equal to zero. However, again, as what I'm saying a while ago, in the first place, we do not know MA, we do not know CB. So again, we will try to use the concept of a unit load method. Instead of applying the total of these forces, since we do not know that one, why not apply a unit load, unit moment, and a unit force here? Then whatever the effect of that, so these are your small f, multiply your force value, and that will be the total effect. Okay, so this again, small f here are just the deformations due to a unit load. So if that is a force, if the redundant is a force, then we will be applying a unit force. Follow the unit of your forces here. That is kilonewton, so we will apply 1 kilonewton. And if you are talking about here a moment, the unknown is moment, we will be applying here a unit moment. Since unit again here is kilonewton and meter, we will be applying 1 kilonewton meter moment at point A. Okay? So again, instead of writing their delta C sub A, delta C sub C, this will be the values, or this will be the resulting substitution to that. Substitute that, and this will be my second compatibility equations. Okay, so as you can see, you have this first equation and this second equation. So if you'll try to look here, that theta AL, since your loads are given, then we can solve actually that rotation at A due to the external loads. And then that the FAA, since we assumed again that the moment here, we will try to assume one unit moment, then this is already known. This will be known also since we will be solving that one. So basically your unknown here is MA and CV, since that FAC also will be solved since we will apply 1 unit kilonewton here. So the unknown in your equation, in two equations, are actually your MA and CV. Your second equation is the same. This will be solved since your external loading is there. That will be solved since we will be assuming a unit load, and that will also be solved. So basically your unknown here in the second equation is MA and CV. Therefore, you have now two equations, two unknowns of MA and CV. You can solve MA and CV. Once we will have that MA and CV, go back here, apply, load that MA and CV, and we have now considered that one as external loadings. Then we will be solving the reactions AH, AV, and EV. Then that will now be the result reactions of our original beam. Okay, so that is how we will be solving this. So again, you ended up with two equations. All we need to do is solve the parts of this equation. So let's start. Let's start by applying your external load. Since there are three cases here, we will apply your external load, find the rotation at A, isn't it? Rotation at A, and then find, of course, the deflection at C due to that external load. And then later on, we will apply the 1 unit moment, find the rotation at A, and then deflection at C. The same, apply 1 unit force at CV, get the rotation at A, and then deflection at C. Okay, so those are the values of your delta, F, and F there. So let's start with your external loadings. Okay, so 120, 120. So let's forget first about your redundance. Only let's focus on the external loadings. Okay, so let's try. Since do not, of course, consider this as a fix, since we already simplified it as a determinate structure. So that is the structure that we will be using in analysis, the resulting determinate structure. Let's first forget about the indeterminate. Okay, since the indeterminate is actually corresponding to the redundance that we will be trying to solve later. Okay, so this is simply supported a pin and a ruler. So if you will try to apply here your 120 and 120 load, this could be my deflection here, and of course, how will we get that one? Okay, that is where you will be using what we recall the moment area or the conjugate beam, or if you are used with other methods, then why not? Okay, but for me, I will be using here the conjugate beam because that is what I'm used with. And of course, if I will show you this, this might also interest you, your conjugate beam method. Because actually the procedure here is simple. All you need to do is draw your M over EI diagram. Okay, so let's start. For us to go to that M over EI, or for us to draw our conjugate beam, we need to start with the reactions, of course, and then draw the V diagram or shear diagram, and then moment diagram, and then that moment diagram, all you need to do is divide that one by EI. If your E and I are constant, then that is the same shape in your loading of your MEI diagram. Okay, so let's start with the reaction. Of course, we'll try to solve that one. That is just moment at A, solve that 120, moment at B, or summation moments, you will solve 120. Or by merely looking at this is symmetrical, so the force will be distributed symmetrically. So you can check that one since that is simple statics. Okay, so 120, you will end up here with the vertical and vertical here to be 120 and another 120 going up. And then, of course, if you'll try to sum it horizontally, there is no such force as horizontal, only that restraint. So it means that the restraint is actually equal to 0, since there is no force where we will be equating that one. Okay, so these are our reaction. Draw now the shear and moment diagram. So positive 120, that is the same all throughout this length, and then we have here 120 going down, so that will go back down exactly, it will be 0. And then there is no other forces all throughout this length, and then there is going down 120, so that will now become negative 120, and then there is no other force, so that will be straight. And then of course this reaction here will put it back to 0, since again that should be equilibrium. So this is my shear diagram. Then of course draw my moment diagram. We do not have moment there, so initially Z is 0. By the way, again, if you'll try to recall drawing shear and moment, we should be doing it from left to right. Okay, we are moving left to right. Okay, so no moment at A, since that is a pin. Do not again mix up with your original situation, your original indeterminate beam. Let's focus on our new determinate beam. Okay, so there is no moment there, so that is 0. And then again, the area in your V diagram is your additional moment, isn't it? So the area here is 120 times the length, which is 5. So 120 times 5 is 600. So from 0, it will be 600 there, but that is 0 degree. It will now become a first degree line, or it will be inclined. And then there is no other moments from point B to D, so that will be the same, constant all throughout up to point D. However, there is a moment due to the shear here, which is actually a negative. So that will subtract from 600. The area here is actually a negative 600 also. So 600 minus that negative 600, or minus that 600 here, will 0 your moment, which is true because that should be 0 moment, since that is not a fixed support. Okay, so again, all you need to do is recall your V and M drawing diagram, drawing that V and M diagram. So this is my M diagram, and then of course all I need to do is divide that one by EI. But if you'll try to look at my beam, the EI are constant. There is no difference in the E and I of this all throughout the length. So actually those are just constant that will be carried. So if you want, why not divide? So that divide this one by E and I, divide that one by E and I, and you will have the same shape and you will have those values. But the reason why I am not doing that is that I will be rounding values and you will be having their decimal values. So that will actually just make our equations. And actually we will just be needing this for the compatibility equation. So you will be having here decimal in your compatibility. So why not take it as a constant? So I will not substitute. I will just write it as all over EI, all over EI, whatever the value is. Okay. So 600 all over EI and the same all over EI. So that is the same. That is my M over EI diagram, which is actually, since I am using a conjugate beam method in getting deflections, this MEI will be my diagram will be my loading of my conjugate beam. But again, do not forget, in your conjugate beam, there will be a transformation of your supports, which if you'll try to recall again your conjugate beam, if your external supports are pin and ruler, that will remain pin and ruler. And there is no internal support, so that will still be the same as that. Okay? If you'll try to recall again your conjugate beam transformation of support, if that end supports is a fixed, it will become free. If that is free, it will become fixed. Isn't it? That is the you can go back to the video of our conjugate beam. Okay, so nothing happens with my reaction, and then I will be loading the M over EI diagram, and that is my loading of the conjugate beam. And then all I need to do, okay, I discussed in the introduction that you can draw the shear and moment diagram of this, but you will expect you will be having their curves and so on and so forth. So as long as you know how to get the area and centroids of curves, then why not? But I explained also that since we are just getting a moment and shear at a point, why not just get that one by getting the summation of the shear and summation of moment at a point. Okay, so I will not be drawing the shear and moment diagram of my conjugate beam. All I need to do is get the moment and get the shear at the point that we are considering. Okay, so I will not be drawing again the shear and moment diagram of that. So since I need, okay, isn't it, if you'll try to recall your conjugate beam or moment area method, the shear at the point is the rotation in radians, isn't it? So we are trying to get the rotation at A. The rotation at A is actually the shear of the beam loaded with the MEI diagram. Okay, so I am using the conjugate beam. So if you try to draw the shear there, actually the shear here is the support, isn't it? If you try to draw the shear in moment diagram, the shear is actually the support. Okay, so if you try to solve first, let's say we do not know yet the support of that, all you need to do is take this one as load. Again, as I've said, that is a positive moment. Before in your introduction, a positive moment will be loaded as a positive load. Okay, what is a positive load? We assume that positive is going up. So this will be trying to sanction your beam going up. This load, MEI, will sanction that one going up. So the reactions will be going down so that it will make this stable. Okay, so actually that is symmetrical. So all I need to do is get the total value or area of this, divide it by 2, or using moment at this point, get that one, moment at that point, get that one. So it's up to you. This is the statics. But if you try to look at the horizontal, there is no force horizontal or any component horizontal, so there is no reaction horizontal. So that is 0. Okay, so again, if you'll try to get the total area of that, that will end up with, okay, this is just a trapezoid, get the area of that, the base plus the base there, get the average, multiply that one with the height, which is 600 EI, you will end up here with 9,000 over EI, the total value here. The total value here will be 9,000 over EI. And of course, that will be, since that is symmetrical, it will be divided here equally, so you will have your reactions 4,5 over EI and 4,5 over EI. Okay, let's just take that as over EI. As long as you made your units coincide with each other, you do not need to worry about the units, okay? So let's just say that is all over EI. So this will be my reactions here. And then, of course, let's start with your theta AL, since we are talking about the rotation due to the external loading and the deflection due to the external loading. So this is what we are trying to solve, since we need this one in our compatibility equation, okay? So the shear at point A is actually the reaction here, since there is no other force exerting at point A. So you draw your shear moment diagram, you will expect that that is just the 4,500 over EI. So that will be my shear at point A, and that is going down. That is a negative shear. So I should consider, which is true again. It should be a negative shear because in actual beam that is, or in the beam that we are investigating, that is a counterclockwise, isn't it? That is what I'm saying. So that is a negative rotation, which is negative 4,500 over EI. So if ever you need the value of that, all you need to do is substitute your E and I. You are given the E and I, isn't it? But you need to make this one coinciding with meters and then kilonewtons, okay? You need to change that one. However, since again, we do not care about the values of this, since later on, you will have your equations in terms of EI, in terms of EI, in terms of EI. All the EI will just be cancelling. I will show you that one later. So I do not need to be solving the exact value of my rotation and deflection. Let's take it as a constant, as a function of EI. Okay, so again, the shear here is the rotation at A. So that is negative 4,500 over EI. And then, of course, we are talking here of the deflection. And again, using your conjugate beam method, the moment at a point, okay, using your conjugate beam, the moment of the loading in your conjugate beam, so if you'll try to draw your moment diagram, the moment at that point is the deflection, isn't it, at that point? So I do not need to draw the moment diagram. All I need to do is find out the moment at this point. So how will I do that? I will cut this one, isn't it? Cut the beam. Consider the left or the right, but you need to, since we are moving to the right, I will consider this left side, the first part of the beam, so that my assumption will still be the same. Clockwise is positive, okay? But if you will consider this other side, because there will be some cases wherein the loading here is simpler, so you will be having a simpler solution, but you need to change your assumption. If you assume the positive clockwise and you are using this, the clockwise will be negative, okay? So that is a recall in your theory 1 again. So all I need to do is get the moment at point C. So what are the loads in my left side, since I am considering the left side of the diagram? These are the loads, the 4, 5, which is rotating counterclockwise, so that is negative. This triangular here, I need to break down, since I do not know the centroid of the entire trapezoid, so I will break down that into a triangle and a square, since that is that has the basic centroids, okay? So what will be the resultant here? I will get the resultant, that is just a triangle, get the area of the triangle, that is 1/5 over EI. And then the centroid of a triangle is 1/3 from the leg, and then 2/3 from the vertex, isn't it? So getting that one, this is a 5, these are 5 meters each. So this is a 5 meter plus 1/3 of 5, so that will be 20 over 3 meters. And that is rotating clockwise, so that is positive. And this is also, if we'll try to get, that is just a rectangle equivalent to 3,000 over EI. So that is just 5 times 600, which is 3,000 over EI. And the centroid of that is exactly at the middle. So if that is 5, the centroid is 2.5. Why am I getting the distance at this point? Because I am trying to get the moment at that point. Okay. Now, try to get the moment. Again, the deflection at that C due to the external loading is the same as the moment of my conjugate beam at that point. Okay. So again, consider clockwise as positive since I consider the left side. So what are the positive? This 1/5 moment, that one 1/5 times that moment arm, and then this 3,000 times that moment arm, positive, and then that is opposite direction, which is counterclockwise of 4, 5 times what is the distance? That is 10. So that is a negative. Therefore, the moment at that conjugate beam at point C, or that is the deflection at point C on the beam itself, is negative 27500 over EI, or 27,500 over EI. Why is it negative? That is true because that will deflect going down. Okay? So you have now your theta AL and delta CL. Okay? The deflection or the rotation at point A due to the external loading, and the deflection at point C due to the external loading. Okay, so we have that already. And then we will proceed. We will try now to start. We are just following this one, guys. External loading, and then investigate your redundant MA, and then later on investigate your redundant CV. Considering unit load, since we do not know this one. So we are done with the external loading. So if you will try to look, we have this one and we have that one already. So all we need to find is this small f, and then you will have now your two equations. Okay, so let's start with the redundant at A, which is a moment. Since we do not know that one, we will be considering a unit moment. Okay, so we will apply there 1 kilonewton meter, since our unit is kilonewtons and meter. So 1 kilonewton meter, that will bend. Okay, that will, since that is my assumption, that will be my assumed deformation. And I will try to find that this is a positive rotation, since that is from tangent clockwise to the beam, and this is positive since it will go up. Okay, so let's start with the reaction again. Solve the reaction. What is just the load there is the moment here. That is just the load. So summate moment at A, you will end up here with A going down, which is 1 over 20 kilonewtons. And then summation of vertical, you will have that to be equal here but opposite direction, since those are the only vertical forces. Okay, and then of course draw the shear diagram. That is going up, so positive 1 over 20 kilonewtons. There is no other forces vertical, so that is the same all throughout, and then this will close that one going back to 0. So we're good. And of course your moment diagram, the moment here, we have a moment at that point, of course, so that is a negative counterclockwise, so that is a negative 1 kilonewton meter. And then this is a positive moment from your shear. The area of that is positive. 1 over 20 times the length, which is 20, will be exactly 1. So negative 1 plus 1 will be going back to 0, which is true since there is no moment at this point. So that is my moment diagram. It is just a rectangle. And then divide that by EI, that will be my loading of my conjugate beam. So your conjugate beam will be the same since your external loading is a simple supports. So that will not change. And then of course, analyzing this as triangular load, all you need to do is find again the shear at point A, that is the rotation here. And then the moment at point C, that is the deflection there. Okay? So that is what we're going to do. But using first the load, find out the reactions. Okay? So that is just the reaction. Get the moment. This is just get a moment at this point using the entire load. And then of course that will end up with the reaction to be 10 over 3 EI. You can check that one. This is just statics. Summation of moment and then summation of forces. And then solving the reaction here, that's 20 over 3 EI. Which is true because the reaction here should be bigger than that because the load is more concentrated in your point A. Okay, so these are my reactions, and summating again horizontal, there is no load there, so that is 0. So you have your reactions. All you need to do is find the shear here, and actually the shear here is the reaction itself, which is again, that is 20 over 3 EI. That is going up, so that is a positive. So it means that is, again, FAA. What is that? That is the rotation of due to 1 kilonewton meter load. That is a unit moment. Okay. So that is my unit rotation, the shear at that point A. And then of course, I will find the deflection at point C, which is again due to the unit moment. So what will I do? All I need to do is get the moment at that point. So actually, if you will try to look at this, we have a simpler loading in this side. But you need to know that you need to assume that the original assumption should be the opposite. However, I will not do that. That is just a way of checking. I will stick on your left side. You can check that one using the right side, but your sign will be negative. Okay, will be opposite. I will still stick on your left side. So I will get this one. This is a trapezoidal again. So I break that down into a rectangle and a triangle. Getting the value of the triangle, that will be 5 over 2 EI. And then getting the value of the rectangle is 5 over EI. And the centroids of that are given by this distance. You can check that one if you want. Okay. Centroid of this triangle is 2/3 of 10, which is 20 over 3. And the centroid of that is exactly at the middle. I mean, this one is exactly at the middle, so that is 5. Okay. So again, I will always assume that clockwise is positive. So this is the clockwise. So 20 over 3 EI. Multiply that one with moment arm, which is 10. And then negative. This is a negative since that is now counterclockwise with respect to point C times moment arm. Let's start with this since that is the first one that I wrote. 5 over EI, the moment arm is 5, counterclockwise, so negative. And 5 over 2 EI, and moment arm 20 over 3 is also a negative. And then evaluating that one, that is 25 over EI. Now I have your FAA, FCA. FAA, FCA. So you have that one now in your equations. FAA and FCA. Okay, those are the partner of my MA. Why? Because I get that one in applying a unit moment in replace to your MA. Okay? Now, all I need to do is find the coefficients of your third term in your equation, which is the coefficient of your C sub V, or your reaction at C, or your redundant at C. Again, we do not know that, so I will assume a unit load, which is now a force, since that is a force. That will deflect my beam this way, and this is the rotation due to 1 kilonewton and the deflection due to 1 kilonewton. FAC and FCC. Again, rotation at A due to redundant at C. Deflection at C due to redundant at C. That is how we will read your subscript. So get the reactions again, that is going up and that is symmetrical. So actually that is just distributed and that is now going down, one half each. Draw the shear in moment diagram, again that is 0. Shear diagram, that is going down, so that's a negative 1/2. That is constant all throughout here, and that will now be going up 1. So negative 1/2 plus 1 will be a positive 1/2. It will now be going on top. Constant all throughout again, and then that will close back to 0. So that is our shear diagram. Moment diagram is we do not have moment here, so that is 0. The moment here is a negative, so that will be 0 minus, what is the value of that? 1/2 times 10 is 5. So that will be a negative 5. And then there is no moment, but this will be a moment. Okay, which is a positive, the same. 1/2 times 5 is, 1/2 times 10 length is 5. So from negative 5 plus 5 will be going back to 0, which is true since there is no moment at this point. So that is my moment diagram divided by EI again. That is the loading of my conjugate beam. The same reaction since those are simple external support. So let's start with the reactions. Okay, so again these are just triangle. You need to get symmetrical. So get the total divided by 2. You will have 25 over EI each. And then get the shear at this point and then get the moment at that point. So if the shear here is the reaction, which is 25 EI. That is your FAC. And then again, the moment at point C is the deflection FCC, which is what are the force. Okay, I will still consider the left side is the reaction and the resultant of the triangle. So getting the resultant of that is 25 over EI, and the moment arm from the centroid of that is 10 over 3. 1/3 of your 10, which is 10 over 3. So again, clockwise positive, so 25 over EI times 10, and then this one which is counterclockwise negative, 25 over EI times 10 over 3. That will be 500 over 3 EI. Okay, now I am complete. We have now the remaining FAC and FCC. Okay, going now to the equations. Theta AL, FAA, MA, FAC, CB. Substitute now the values. Okay, if you'll try to go back to the slide, theta AL is negative 45 over EI. Okay, you can check that one so that I will not be sliding back this one. It will not waste our time. We already solved that, this one. Negative 45 over EI. So you can always check back. Okay, so substitute, that is negative 45 over EI, and of course, FAA, we solved that already to be 20 over 3 AI. MA is the unknown. FAC, that is 25 over EI. We just solved that one in the previous slide here. This one. And of course, your CV is the unknown. So equate that one to 0. Simplify, this is what I'm saying. The reason why I did not multiply my EI, because that will just be a waste of time, since if I will try to look at this, since these are just numbers, factor out your EI and EI, making this one similar fraction, isn't it? Make it 3 over EI, so that will be multiplied to 3. This will be multiplied to 3, so that your 3 EI will be factored out and then multiplied to 0, which will become useless. Okay, again, make this as the same fraction all over 3 EI. So multiply this by 3, multiply that by 3, since there is no 3 below. Okay, and then the 3 EI will be cancelled to 0, and then transform whatever this 4 5 times 3, which will be 13 5, it will become positive on this side since that is negative. And then that is 20 still, and that will be multiplied by 3, since again we will make that 3 EI, so 75. So this is my equation 1. So you can check the algebra of that. Equation 1. And then going back to the second compatibility equation, substitute your deflections. These are rotations, isn't it? These are now deflections. So again, you can check that one. This is what we solved. Substitute. So negative deflection due to the load, and then positive deflection due to the moment, the 1 kilonewton moment. Meter moment, and this is due to the 1 kilonewton force. And then again, making that one the same fraction, this make that 3 EI, and then cross multiply 3 EI will be useless. You will end up with equation 2. And then of course, equation 1 and equation 2, the unknowns are MA and CV. So algebra, that is just algebra, solved simultaneously. You will have the MA to be exactly, okay, this is the good thing. Since I did not substitute my EI, so I did not end up with rounding values. So I had this exact value. This is the exact value of MA and the exact value of CV. But if you want the decimal, then that is the decimal values. And then, okay, now I already know this redundance, isn't it? These are your redundants. Go back to the original beam. This one. MA and CV are my redundants, and I already solved that one from your compatibility equations. Now I will apply it as a load together with your 120, and then solve that AH, AB, and EV using statics. Okay, since that is now the remaining unknown in our problem. Okay, so substitute that MA, substitute that CV. You have only 3 unknowns, 3 reaction unknowns. So summation horizontal, again AH is, there is no force horizontally, so 0. And then summation moment at A, you can check the algebra later. So 120, what are the forces? I assume again clockwise is positive. 120 times 5, and of course the 120 times 15, since we are getting moment at A. What else? Of course, the moment at A itself. There is no moment arm if you are summating a moment, which is actually counterclockwise, so that is negative. But I will use not the rounded, I will use the exact value, so that I will get also the exact values. So that is the 90 over 7, a negative, since that is counterclockwise. And of course, what else? Your reaction CV, which is I will use the exact value, 1020 over 7, the moment arm is 10, counterclockwise, so negative. And then of course your unknown here, which is the reaction at EV, which has a moment arm of 20 and negative, since that is counterclockwise. So equate that to 0, equilibrium again. So solving for EV, that is just algebra, you will end up with 285 over 7, or in decimal, that is 40.71. And then, of course, summation vertical, the only remaining unknown is AB. So AB going up, which is CB, and then EB, which is also going up. And then, of course, the going down to 120. So 2 times 120, you will end up with AB to be 375 over 7, positive. So my assumptions are the same. This is what I'm saying. All the values are positive since, again, I tried to target the correct assumption. But once you made a mistake in assuming the direction, that will just be giving you a negative value. It means that the negative there, it means that your assumption is wrong. But the value will be the same. All you need to do is flip your, let's say, I ended up with a negative AB. All I need to do is I will flip the direction on the actual beam. So now we are complete. You have your MA, the moment at that fixed support. This is the original beam. This is the indeterminate beam. Okay, that is the moment at A. You have this AB at A, and you have that horizontal to be 0, and you have that reaction. Sorry, this is supposedly. Sorry, I will just change that one. Okay, so again, sorry, I just changed that one. That is supposedly originally ruler. Okay, so again, that's it. You have this CV, or the reaction at the ruler, to be the CV, and we have it here. And then, of course, your EV, you have that there. Okay, so now we already have all the reactions of our indeterminate beam. Then, let's say you need the shear and moment diagram of this beam. Then you can now draw, since you already have now your reaction. You can now draw the shear diagram, you can now draw the moment diagram, and then you can, of course, solve the deflections and rotations in any part of the beam. Okay, so that is now using your consistent deformation. Okay, so let's have another example, but of course we will be considering the same beam, but this time we will be using different redundance. Okay, so a while ago I considered, okay, this will serve as our example number 2. Instead of drawing another beams and another diagrams, let me just use the same, but of course different redundance. Okay, so a while ago our redundance is your MA and your CV, but this time I will just make it as a cantilever beam. So my reactions at the ruler will be my redundance. So you have these 3 reactions at this fixed support, which will be my reaction on the resulting determinate beam. So that is still stable. Why? Because it will not move horizontally, it will not move vertically, and it will not rotate because of that MA. So that is stable, and my redundant is my C sub V and then E sub B. Okay, so the same procedure. That's we already choose our redundance, and we already drawn your determinate beam. Now formulate the equations of compatibility. There are 2 redundants, so 2 equations again. So what do we know is that at point C, that is supported. So of course, the rotation here is not 0, since that is not fixed, and the rotation at E is also not 0, since that is not fixed. So we will not be using the equation of rotation. A while ago we used that one since that is fixed. Okay. Now what am I going to use is the deflection at C, just like a while ago, and the deflection at E, which is supposedly both to be 0, since that is originally supported by rulers. Okay. So let's start with the C. Deflection at C is 0, since that is support. So again, break down the effect of the external loading. And then, of course, the effect of your redundant at CV. Let's start with the redundant at CV, and then the redundant at EV. So again, the same procedure as a while ago. So the external loading, if that will now serve as cantilever, okay, this will be the flow, or this could be my deflection, or the deformed shape of my beam, or that is the elastic curve. So this is the deflection at C, and that is the deflection at E, due to the external loading. So I can solve that one. Deflection at C due to the loading, and deflection at E due to the loading. So this will be my 2 equations here. Again, I will be explaining that one later. And then, of course, apply the redundant at CV. You will be having this deflection or deformed shape. So that is not, these are negative. but this will now be positive since now the force is applied upward, so that will deflect going up. So your deflection is going up, so that is positive deflection at C and then positive deflection at EC. However, in the first place, we do not know your redundant CV, so again, we will be considering a unit force at point C. Which that's why instead of having that deflection at C due to redundant C, you will be breaking down into unit deflection and then multiply to the force, and then later on also your unit deflection due to your redundant at E, and then of course multiply that one with your EB. Okay. So the same will happen in these two equations. So how about here on the redundant at EB? Again, we do not know that one, so assume later on a unit force, but that will eventually make this one, this beam deflected going up. So again, a positive deflection at C, a positive deflection at E. So summating all of this, at C, summating all that deflection, this is negative, that will cancel out by this two positive. So that will end up with 0. So you will end up with your first compatibility equation, and the same thing with your point C. At point C, a negative due to the load and a positive due to the two redundants, it will cancel out and that should be 0. So you will end up here with the second compatibility equations. So eventually the unknown here in your two equations is CV and EB. We will be solving that coefficients one by one. So CV and EB, so we will be solving this. Okay, so let's start with the, where's that? Let's start with the external load. Okay, so this is the external load. Let's try to find the effect of that at C and E, the deflections at C and E. So these are your external loads. So first again, solve the reactions. These are the only reactions here. So summation vertical, that is 240 going down. So you will have your reaction going up to be 240. Summation moment is 120 times 15, 120 times 5. You will end up here with 2400. This is clockwise, so that will be counterclockwise. And then summation horizontal, your horizontal reaction is 0. So you have your reactions. Draw your shear and moment diagram again. So the shear here is going up, which is 240, and then that's constant all throughout, and that will go down 120, so that will be a positive still 120, constant all throughout, and then that will go down again another 120, it will zero out, and that will be continuous. So there is no shear from point D to E, which because again there is no support and there is no forces here. So that will just deflect, but there is no stress, shear stress from D to E. And then the moment diagram, let's start. There is a moment at point A, so there is already a moment there that's counterclockwise, so a negative 240. And the area here is 240 times 5, you will end up there with 1, 2. So negative 1, 2, and that is a positive. Negative 24, 2400 plus this positive 1, 2 will end up a negative 1, 2. And that is straight, so this will become inclined. And then of course negative 1, 2, what is the area here going to that point? D is 1, 2 times 10 is also 120 times 10 is also a positive 1, 2. So negative 1, 2 plus 1, 2 is 0. That will be 0 there. So again, there is no stress, moment stress or flexural stress from D to E. So this is our this is the effect of our external loading only. Then of course, draw now your conjugate beam. Okay, as you can see, this is a fix. So according to conjugate beam support transformation, a fix at the end will become free, and the free end will become fixed. Okay, and then the M diagram divided by EI, and that will be our loading. So that is a negative moment diagram. So this is a negative loading, going down loadings. So this will be again, since we are investigating deflection, so we will get the moment at C and moment at E in your conjugate beam. So moment at C, I need to, again, I will stick in using my left side. So you can use your right side to check again the values that we had here. But of course, you need to change your assumption of direction. So since I will be using this left side, I need to break this down into a rectangle, triangle, a rectangle, and triangle. So these are the values. And of course, these are the moment arm. You can check that one. I will try to recon the distances to this point C, since I will be needing that point C later on. And then to get the deflection at point E, I will be getting the moment of these forces together with the remaining here. A while ago, I do not need that, since in this left side, these are the only forces that I need. But getting the moment at point E, I will be needing that one, so I will be getting that one. So again, these distances, all we need to do is add 10 meter going to point E if you will be getting later the moment of that. So again, positive 3000 times this one. I'm sorry, negative, since I assumed to be the clockwise to be positive. So this is a counterclockwise with respect to C, so that is negative. And a negative 6000 times 7.5 counterclockwise. This one. And then of course a negative 15 times this 10 over 3. And then a negative 3000 with that 2.5. And calculating that one, these are all negative, will end up with negative 82,500 over EI, which is the deflection at CL, which is true because in my assumption that is going down, so negative deflection. And then now get the deflection at E, that is the moment at E. So now I will be momenting all the forces plus this force here this time, and then the distances, all I need to do is add 10. Okay, so as you can see, the values are just added by 10. And then these are the forces. So again, they are all counterclockwise. There is no clockwise moment, so these are all negative. And then that will end up with 230,000 over EI, a negative, since that is deflection negative. So that is our external load. You have your deflection at C due to the external load, and deflection at E due to the external load. Okay, proceed with the redundant. Let's start with the redundant at C. Apply a unit load again, since we do not know the redundant. So get the reaction. So that is the only vertical force, so that is the same but opposite direction. Horizontal, there is no force, so that is 0. Summate moment, so that is counterclockwise, so your moment is clockwise. And that is 1 times the distance 10, so that is 10 kilonewton meter. Now get the FCC and FEC. These are small deflections. So small deflections will be getting the moment on your conjugate beam. So let's start with the shear diagram. Negative 1, the same all throughout, and that will be going back to 0. And this is unstressed. And then moment diagram, we have there positive 10, so positive 10, and then the area here is negative 1 times 10 is negative 10, that will be 0 there, and unstressed. Okay, so this divided by EI, that is our load in our conjugate beam from fixed to free fixed. Okay, get the moment again at point C, that is the deflection, small deflection at point C. Okay, so get this, that one, that is 50 over EI, moment arm 20 over 3, moment is clockwise, so that is positive deflection, which is true. And then moment at this, plus 10 to that 20 over 3 will be 50 over 3, clockwise still, so that will be 25 over 3 EI. Okay, now let's try to apply your redundant at E, which again a unit load or unit force. Vertical force only is 1, so that is the same but different direction. Horizontal is no force, so 0. This will give us a moment about A to be counterclockwise. 1 times 20 is 20, the distance which is 20. And then counteract that with clockwise, which is 20 kilonewton meter also. Draw the shear and moment diagram. So negative, that is all throughout, and then that will be zeroed by this positive 1. And then original positive 20 kilonewton meter, and then of course this moment here, since there is no moment along, so that's the only moment here, which is a negative 1 times 20 will give us negative 20. So 20 minus 20 is 0, and originally V diagram is straight, so that will be inclined. Okay, divide this again by EI, 20 over EI. Later on, since I will be getting a moment at C, I need the value of the stress or the load here at point C. So actually, since that is a triangle and that is at mid length or mid base of the triangle, that's actually by ratio and proportion 1/2 of 20 over EI. So this is 10 over EI. Again, my conjugate beam from fixed to free and then free to fixed. Then again, summate moment at C. So what are the forces? I will break this down into rectangle and triangle. So this is the triangle, this is the rectangle. So the centroid of that is 2/3, since that is the vertex, so that is 20/3, and that is exactly at the middle, so that is 5. Okay. Summate moment, that is all, those are all counterclockwise. There is no clockwise, so that is, these are all clockwise. There is no counterclockwise, so that is positive. 50/EI times the 20/3, and then of course 100/EI times the distance 5. You will end up with 25/3EI. Positive, since that is a positive. And then summate moment at point E. So now I will include this part of the load, since again I did not include that a while ago. But again, as I'm saying, you can, if this is complicated, you can use that one. Or you can use it as a checking, but you need to change the assumption of the direction. So moment at this, I will just add 10 with the distances of 50 and then 100. So I just added 10 there. But I need to add this load here, which is 50/EI, and that is 20/3 distance. So all clockwise, so positive, so that will be ending up with 8000/3EI. Now I completed my equation. So substitute the values, you will end up with equation 1. You can check that one, okay? But I am pretty sure since my answer is the same. So this is my equation 1, and then substitute the values again. Simplify equation 2 simultaneously. Since the unknown here, the redundant that we try to choose is your CV and EV. Therefore, that is what we will be solving using the compatibility equations. And CV is 1020/7, which is 145.71. That is the same as a while ago. And your EV, the other redundant, is 285/7 or 41.71, which is also the same as a while ago. We can compare that one. 14571, 4071. Let's go back to the first result using the first solution. Okay, so 14571 and EV is 4071. So we're good. So it means that solving the rest will be the same. Okay. So that's it. Solving your, of course, horizontal, no load horizontally, so that will still be 0. Solving the moment at A, get the moment about A. 120 is clockwise, this will now be positive. MA is, I assume that one to be counterclockwise, so that is a negative. And then of course, reaction at CV is negative since counterclockwise, and reaction at E is negative counterclockwise. End up with 90/7, 900/7, which is the same 128.57 and the same direction as a while ago. So we're good. And of course, remaining is AB, summate that one vertically, and then solve that one, that is 375/7, that is 53.57. 12857, 53.57, let's check. Okay, so M is 12857, we're good, and then AB is 53.57. Okay, the same. So that's it. That is my example for applying consistent deformation method on beams. Okay, so again, do not forget on the procedure. That is the important there, is to follow the procedure. So these are the important concepts here. Stability of the system should be considered in choosing redundants. Okay, so that is what I'm saying. Always check the stability. Do not just be choosing the redundants. You need to see that the remaining restraints will still be holding your structure to be stable. Okay, and then of course, since you do not know in the first place the directions of the reactions and the redundants, all you need to do is assume a preliminary force and couple directions, and of course verify the sign of this later on in your results. If that is a negative, it means it is just the opposite direction. Okay, so that is your consistent deformation method analyzing indeterminate beams. So in the next video, we will be proceeding with frames and trusses. So you will be having activity. Please check that one in your canvas. So thank you very much for watching.